We could save tens of thousands of lives if everyone would just wear a mask.
There is no evidence that they protect people who are not sick.
Yes, vaccines do harm people.
The safety and the efficacy of this vaccine.
No, the out of doors is safe.
Public events will be prohibited.
COVID-19 can be.
It could be the flu.
Ever since the coronavirus pandemic started in early 2020, there's been fake news circulating all over social networks. The vast amounts of COVID-19 misinformation can be explained by the insufficient knowledge among the scientific community during the initial stages of the pandemic. Misinformation spread on the platforms Facebook, Instagram, Twitter, and IGTV has resulted in individuals making uninformed health decisions. The main objective of this paper is to compare different supervised learning and deep learning models and determine the best model for classifying short text and unbalanced data as real or fake news. The reason why we wanted to do this is because a classification method that accurately identifies short text and unbalanced data as false information will aid in preventing the spread of COVID-19 misinformation.
In this slide, we can see the overview for the materials and methods, starting from data collection, data pre-processing, vectorization, and classification. We chose the COVID-19 healthcare misinformation dataset for our classification model. Vectorization. The next step was to convert the text data into numerical form. And for this, there were two methods employed.
Concerning text classification methods, traditional supervised learning involved using variables about tweet features such as user verified status to determine if a tweet was real or fake. The parameters used for the naive Bayes models and Cannon models are shown in the current slide. The parameters used for the SVM, random forest classifier, and Gannon models are shown in the current slide. A linear kernel was used for the SVM model. We also decided to use an RNN model with a bidirectional layer. This is because it would allow the model to look at the word ahead before encoding the current word. Additionally, a new model was created where BERT was used for word embedding. This would allow the model to understand the context between words a little better. Finally, we performed sentiment analysis using Vader. And in fact, an algorithm was developed based off of this. What happened is that if the RNN probabilities were between 0.45 and 0.55, then those probabilities, along with the sentiments, were used in a logistic regression model to create final probabilities. Otherwise, the original RNN probabilities were used.
With the results in the exploratory analysis, we can see that the jump in the total number of real texts sent in April coincides with when COVID-19 cases rose globally. A similarity that is seen between the top 15 retweeted fake hashtags in 2020 is a relatedness to COVID-19 news and government policies. Lastly, the high standard deviations seen between the months of April to June indicate the viral nature of social media.
Gaussian naive Bayes, logistic regression, and random forest models were used to predict whether a tweet was fake or real using select tweet features. The random forest models provided rankings on feature importance, and this is the model performance, the accuracy, precision, and recall, and F1 scores.
3 deep learning models were created: a traditional DNN model with no word embedding, an RNN model with regular word embedding, and an RNN model that used a BERT model for the word embedding step. The results in the testing data can be seen here. The results in the supplementary dataset can be seen here. An example of word embedding for the word hoax can be seen in this slide. Words similar to hoax are graphed closer together. Before the final algorithm was applied to the test dataset, the correlation between the different tweet features and probabilities generated by the RNN model were calculated as shown in the table. These were the accuracy, precision, recall, and F1 scores of the final algorithm on the original test data and the supplementary dataset.
Discussion. In this slide, we talk about the overview of the discussion. confusion matrix. The accuracy, precision, and recall and F1 scores are all derived from the formulas as you see on the slide. And looking at a confusion matrix helps to conceptualize what these values mean.
From our exploratory analysis, we can see that the data is highly imbalanced, as the number of tweets containing real information far outweighs the number of tweets containing fake information. Knowing this influenced the types of models that were chosen for our classification. When looking at the average retweet count in 2020, the number of fake tweets that were retweeted increased exponentially from January to June 2020, probably due to a lack of monitoring concerning COVID-19 information. A limitation to the dataset is that the data needs to be constantly updated. Seeing as the content comes from a social media site, there will be new emerging words and concepts. So in the future, the model needs to be trained on newer data in order to capture these new emerging trends. This also explains why the RNN model was chosen as our best classifier, as it is the most flexible and able to handle these new words and concepts.
For traditional supervised learning, using only tweet features proved ineffective, but the model showed us that the most important variables all have to do with how active the user has been with their Twitter account. The naive-Bayes models were the most scalable, and the random forest model could identify key themes, but it wasn't able to handle new words, and the KNN model was not able to deal with high-dimensional text data. In the top 20 features from the random forest model, the names of popular Twitter users were deemed as important. Interestingly enough, the names of popular COVID-19 conspiracy theorists also appeared. This means that with regards to social media data, it's really important to identify the accounts and individuals with a large audience, as they're the ones with the most engagement and they're the ones who will be spreading the most information. The SVM model performed the best on the training and supplementary datasets because it handles high-dimensional data well and is robust against overfitting. The issue, however, with all of these models is that they use a bag of words representation, which doesn't leave room for new words to be analyzed and doesn't consider the context between these words, which is why we see overall poor performance on that supplementary dataset. Another thing to consider is that the training data needs to be updated constantly. Overall, the dataset in this paper only looked at the year 2020 and tweets in English, but in the future, more work should be done to train the model over newer data in order to better capture emerging trends and to apply these models to non-English language. The RNN model performed well on the original dataset, and out of all the models, performed the best on the supplementary dataset. This is because the RNN model was trained using class weights to handle the imbalance in the original data, and it included an embedding layer. Word embedding is when words that are similar to each other are encoded with similar vectors, thereby meaning that when they are plotted, they're plotted closer together. This helps the model to understand the context within which the words are used. Let's take, for example, the word hoax from the random forest model. What is very interesting is that the words that appear near the word hoax and the word embedding are also considered significant features in the random forest model. This shows that various models are able to identify which words are important. What makes the RNN model stand out is its ability to encode words within the context of the tweet. The best model needs to be one that is flexible enough to handle new words and phrases that it has never seen before and to understand context. It is a necessary requirement because social media data is constantly changing, and the ideal model should be able to keep up with these changing trends, which the RNN model is able to do.
The BERT model was used to perform word embedding using transformer encoder architecture, and then an RNN model was applied afterwards. Although the BERT model did perform well with a supplementary dataset, it did underperform with respect to its F1 score, as a pre-trained model was used. So although the corpus is vast, there are many words in the original dataset that did not appear in the BERT corpus. Next steps for our group would look at fine-tuning the pre-trained BERT model to add unique words to the BERT vocabulary.
Final algorithm. So when the algorithm has been applied to the test dataset and the supplementary dataset, the results were mixed. Although it is too early to conclude that sentiment must be used to help classify the tweets, the preliminary results in the paper demonstrates that the sentiment and the other features of tweets may have a role to play.
The SVM model was the best traditional ML model, but the RNN model was the best model overall. The model chosen for detecting fake news will ultimately depend on the size and nature of the dataset, scope of the problem, and computer limitations.
Our team was able to develop a prototype app called TweetScan. It demonstrates how various models would be utilized in real-life situations. We chose to deploy our models in the format of an app due to 1. Ease of access, as you can easily type in short text into the website to determine if the information is real or fake, and 2. For its practicality, as it can be used on multiple devices.
Future plans include creating our own sentiment model using various statistical models. Developing a sentiment model using the current data will introduce COVID-19 related vocabulary to the model, which will improve its ability to accurately predict sentiment